So I'm going to talk to you today, very similar to the talk we just saw from Roche on our self-driving lab approach using Bayesian optimization at Takeda. Quick background first on my group. I'm in the synthetic molecule process development group. So it's a process chemistry and engineering group within R&D. We focus on small molecules and span across early process development from or process development from early to late, all the way to manufacturing. We need to find new routes and scale up existing routes to enable this process development that we do in our group. And really, just like we just saw in the last talk, this involves exploring large parameter spaces. In this case, I picked a reasonable number of different conditions that would lead to 13,000 possible combinations, although we just saw examples of up to 40,000. So, this is large spaces that need to be explored. And we need to do this as quickly and efficiently as possible to give our chemists or chemical engineers the answers to the question of what should I look at next? How do I proceed forward with optimizing this scale up? The answer to that is partly high throughput experimentation. So you saw some Unchained lab stuff in the last presentation. We use Unchained as well to run high throughput experiments. Personally, we do it slightly larger scales and lower throughputs than, for example, what we just saw, to help avoid some manipulation issues and give us better quality data. And then we combine this with algorithms, specifically Bayesian optimization, with a node code platform called Itinerary that we use at Takeda to enable decision making. And that really lets us, combine our expert chemist and engineer knowledge with the exploration and exploitation of these tools to find hits and move forward quickly. This is our overall workflow. We've got a lot of stuff here. I'm not going to have time to go into almost anything really, but really quick, we start with our ELN entries and knowledge of our chemists, and use some other tools as well. Create the DOE in both Catalyst, a web-based ELN and analytics platform, and Itinerary, our Bayesian optimization platform. Perform the screening with Unchained lab robots, analyze the data, typically HPLC data, since this is process chemistry for drug development, and then analyze the data with Itinerary and Catalyst, and then send it back around for the typical design, make, test, analyze cycles. Giving you some pictures of what that looks like in the software. This was an example of an acid chloride amidation where I can't show you the molecules, but we set up all the compounds in Catalyst, the web-based platform we use, as partly ELN here, but then data analysis and connection to other tools as well. So here you can see we've, from the compounds that I put into it, decided what would be my quote unquote DOE. I say quote unquote because we're using Bayesian optimization, not typical DOE. We send this, the factors that we want to explore in the parameter space, to our Bayesian optimization platform, Itinerary, which we pay for their services. And then Itinerary will pick the conditions for us and then send it back to Catalyst. So in Itinerary, that looks like the following. It doesn't have any kind of chemistry knowledge the same way that Catalyst does. So we would just have, the names of the parameters that were sent to it. It picks the combinations that we want to run. We'll do a combination of categorical and numerical parameters, so things like concentration, equivalence, as well as the identities of compounds. Here you can see that Itinerary has picked for us, in this case, the first 24 experiments that we're going to run, and then that gets sent back to Catalyst, and then we map that out into the wells that are going to be run. Again, we do typically 24 at a time in about half a milliliter to a milliliter scale. This is then run on an Unchained Labs robot. So here you can see two robots in the lab that we've got connected together. I'm not going to have time to show you these full videos, but one of the robots can add powders, liquids, and cap the vials. So here we've got it capping. The other one can do just liquid handling and moving vials and plates around. So here you can see it taking some solvent. It's going to add that to the vials on the right. It can also pick up and move vials around for the purpose of imaging them with a camera, or we've recently added a Raman probe as well to look at our vials. Additionally, we've got a mobile robot that, again, for a short talk, I can't show you this whole video, but this picks up the samples of vials, in this case from an antechamber between two Unchained labs in an isolator, picks up the HPLC vials and takes them to the HPLC for later analysis. I'll end here just by showing you that this is what we typically expect out of our 3 rounds of 24 experiments. We're very happy with how our Bayesian optimizer performs, and might have some okay hits in the first round, better hits in the second round, and then almost always we have some good results in the third round here, with, in this case, area percent is what we're looking at. And just I'll end here by showing you that itinerary is really useful, not just for selecting the conditions that we're going to run and being our Bayesian optimizer, but also visualizing the design space and the values of what we're getting out of it at the end. So here's a hyperparameter plot reducing down to 2 dimensions all the different variables that we were screening. I really like parallel coordinate plots as well for visualizing what's best and worst. And the best result that we've had so far internally screening is we found the same result in 3 rounds of 24 experiments that a CRO did in over 2 months of running the same analysis and trying to optimize the same conditions. So with that, I'll thank my team and pass it back to Jacob.